So actually the lectures are on modified gravity theories. What I will do is that I will make some introduction first, just to be sure that we have all the same definitions. So I will talk about a bit of GR and cosmology today. And then after that I will start going more into the details. I will not make a review of the different models of gravity which exist, because there are plenty of models. And that's not the idea. You can find many reviews about it. The idea is more to know about three things. One is motivations. Why do we study some models more than some others? So mostly on the motivations. Second is on the constraints that we have. We have constraints in the laboratory, constraints in the solar system, constraints from black holes, constraints from cosmology. So we are going to look a bit on all these constraints, what they say about physics. And the third one is to learn some techniques, actually. So this will be also during tutorials. We'll learn some techniques on how to calculate, for example, in modified gravity theory or even in GR, what is the speed of propagation of gravitational waves. How do we know that a theory is well defined, that there are no ghosts in a theory? How do we study the background, cosmology, for example? This we will see that with dynamical system analysis. And also today, for example, for the tutorial, will be mostly on some aspects like, for example, the age of the universe. We know that the universe is 13.8 billion of years. How do we know that? How do we measure that? So we'll do these calculations today, and tomorrow we'll see how from the constraints, mostly from supernova, which are some type of stars actually, which explode, and we will see if, how do we know that we say often that there is 30% of matter, 70% of dark energy? How do we know that? So again, we will link that to observations. So the first lectures will be pretty general lectures actually. I will start really on some definitions of general relativity. So it might be very boring at the beginning for some of you who already took classes in GR, some cosmology, and then we go more and more into the details until the end, where I will explain mostly the interesting aspects of these theories, and also the sites which are showing that these theories are viable or not. We'll have a discussion about it. So this will go until Saturday, actually. So please feel free to ask me any question, and the idea is really to have interaction on that, not just one side actual lecture. I'm sure that if you have a question, many others will have also the same question, so you are just helping others actually by asking. So feel free really to ask. And the most difficult one is the first question, but so just go ahead and then the other questions will follow. Okay, maybe yes, I can start now, or maybe just my name or something like that, how to pronounce it. So that is my first name. You can use just my first name. There are different pronunciations that you can use. I'm originally from Morocco. I grew up in France. So I heard all my life two pronunciations. One is the pronunciation from Morocco, which is Ardouan. So if you can pronounce that, that's perfect. The pronunciation in France, which I've heard also all my life, is Radouan. So, and you can take anything in between actually, that's okay for me. So either Ardouan or Radouan, as you wish, it's fine. So now actually I was in India often. I did a postdoc in Ayuka. So I was visiting this place quite often, working principally with Sami. And I came back often actually. So now I'm in Chile, in another continent, South America. And yeah, so again, it's really a pleasure to be here. So let's start actually with so I will be here actually in the office just here. So if you have some questions, you can come to talk to me. I would say that better, if you have some question, better to ask it here because it can help others also. But if you don't feel comfortable to ask, I mean, just come then. After that, we can talk in my office itself. But better to ask in front of everyone because everyone can benefit from that. Okay, so let's start with general relativity, some very general definitions. So the theory was developed by Einstein. So yeah, about the notes. I'm actually currently writing some notes. I'm now at some 50 pages, but I will add a bit more. They are handwritten. So sorry for that, I didn't finish them yet, so they didn't have yet my notes, but you will have them. So we will scan them as far as I understood, and you will all have a copy of it. So if you want, you don't need necessarily to take notes. You can just listen and try to understand things. If you feel more comfortable to take notes, you can take notes. The reason why I'm writing on the blackboard is because it's, if I do a PowerPoint, it passes too fast and you don't have time to calculate it. If I write, of course, the brain goes at the same speed than the writing, so then you can understand things. And so if you don't want to write and just listen and try to understand, it's fine also, of course, you will have the notes. I will try to finish them as fast as possible. Okay, so I suppose you all know GR? Some people didn't study GR? No? Yes? Okay. So let me just remind a few basic things about general relativity. So it's a theory developed by Einstein, 1915. It's a geometrical theory which says more or less that the space and time gets curved. So because of that, we have to go to something which is not flat. We cannot use Euclid geometry, but we have to go to a curved type of space-time, and then we go into a mathematical structure, which is the Riemannian space-time or pseudo-Riemannian space-time. The idea of Einstein about that is based on some experiments, some Gedanken experiments, thought experiments that he had. And principally they were based on elevator, saying that what's happening if someone is in an elevator. You are in an elevator, you are free falling, and what's happening in this case is that you don't feel gravity. You are just levitating actually, and you don't feel anything. If you have an object which is in the elevator at the same time than you, and both of you are falling, you are going to fall with the same acceleration. So actually the two objects will be next to each other and nothing happens actually. So he was understanding that gravity in some way is the same thing than acceleration. So he tried to understand gravity by experiments where he produces some acceleration. If we take some elevator like this, and we have someone in this elevator, and we produce some acceleration to the top, this person here will feel some gravity actually going down, so it's equivalent to have some gravity actually. So in that sense, he understood that there is some equivalence between acceleration and gravity. So his experiment was the following, for example, is to say, okay, let's suppose that we have an elevator and we have some acceleration. This is called the equivalence principle. Let's suppose we have an elevator going up and there is a light ray coming here. So this is a light ray. During actually the acceleration, so the elevator goes up, so the light ray enters here, but it will exit something more down because the elevator goes up, so it will go down like this here. So for the observer inside, he will have the feeling that actually the light ray does something like this. Of course, light ray goes straight. It's just that the elevator goes up, so it enters here, but at the same time the elevator goes up, so it will exit a little bit more down. But for this observer, it looks like if the light ray actually curves. So because he thought that, okay, acceleration and gravity are the same, so it should produce the same thing. When there is gravity, light ray should curve. Now, this is something that we know very well, which is observed. This is called lensing. There is weak lensing, there is strong lensing, etc. And this is used in astronomy every day. And actually, I'm not going into these details about astronomy, but interesting things. For example, you have a galaxy, And let us suppose we are here, we are observing, and there is some object here. This object is sending some light, and light actually bends because of this galaxy. That is exactly this effect. And it is called weak lensing. So us, when we observe the sky, we can see actually twice the same object. The same object here, we observe it in this direction, and we observe it in this direction. We can observe it 3 times, 4 times, etc. We can even observe a circle. And the very interesting thing is that these 2 parts, this is a way to see that that is correct, actually. It has been shown just a few years ago, actually 1 year ago. It's an interesting paper where they were showing, okay, actually this path is not the same distance than this path. For example, we can say that the galaxy was a bit bigger like this, so it does this. So actually the light takes a bit more time to come through this path than this path. So what's happening is that in this case, we will receive first the light from here, and then this one. So you see twice the same object in the sky, but they are not the galaxy at the same moment. One is a galaxy which is seen 1 million years ago. The other one was 1.1 million years ago. So you see it at different moments. So what they observed is the very interesting thing, is that in this galaxy, there was an explosion of a supernova, a star which exploded. And where they said, okay, these 2 things that we see on the sky is exactly the same object. We have observed an explosion. So in December 2016, we are going to observe the same explosion in that direction of the sky, because it's exactly the same object. It's just that we don't see it at the same moment. So they made the prediction in December 2016, we should, in this direction, in that galaxy, observe an explosion of a supernova, because it's exactly the same object, just shifted in time. And in December 2016, they observed it. So that is a way to prove also weak lensing. So it's a quite interesting, actually, and strong thing. And now this is the way that we observe dark matter and all these things. So weak lensing is extremely popular. And that comes just from this thought experiment by Einstein, actually. Okay, so I cannot go much into the details of general relativity. So let me go just directly to the definitions and what we are going to use. So the action, because in physics we define always an action, and from that we write the equations of motions and things like that, actually. So this is the action of general relativity. So if you want, this is the Lagrangian. This is what is called the curvature scalar. This is the action for matter. So you have some matter in the universe, and that matter produces some curvature here. And this is the metric. So as we know, the metric is used to measure distances. This is the speed of light, and this is the gravitational constant. So just from the constants, we understand that this is a theory of gravity, because there is G, and it's a relativistic theory, because there is C, the speed of light. But this is not a quantum theory, because there is no H, the Planck constant. Okay, so this is the action of general relativity. You can work it out and find the equations of motion. I will come back to that later on, because actually this action is not well defined. You have to add an additional term. I will explain that later on, which is called the Gibbons-Hawking term. And this is going to be very important for my class on Thursday or Friday. But I will come back to that later on, because that is not a well-defined action, in the sense that if you make a variation, we always get some term and we say, yeah, this term is 0, but actually it's not 0. So there is a problem with that, but you can add a boundary term which takes care of that, and then it's mathematically well defined. I will come back to that on Thursday, but for the moment I will just continue with that. So this is the standard thing. G, as I said, is the metric. You can measure distances with the linear element, which is this. So this is the distance between two nearby objects, and G mu is the metric. And R is just the the trace of the Ricci tensor. And the Ricci tensor is defined by the Christoffel symbols. This, I have to look to the formula. It's a bit long formula. So you have the variation of the Christoffel symbols Okay, and let me write the, so this is just a notation, means the variation with respect to x alpha. And let me finish this other notations I will use with the Christoffel symbols. So let me just now erase that, just to have everything on one blackboard to see what definitions I use. Definitions are very important because according, each book has a different definition. I'm using the definition by the, in the book by Wald. If you take Mislinton and Wheeler, the definition is different. But anyway, the physics doesn't change, of course. But the calculations in between can be a bit different. Okay. So imagine that you have some metric, you know.
So the curvature and metric component of action, are they independent of each other?
Which one?
Curvature and metric component of action.
The curvature R and the metric component. Which metric component?
Action is in two parts.
Ah, the matter part.
So
Yeah, it's a different thing. That the matter part you can add then. Yeah, this is the part of curvature, okay. And the other one is matter, so you can add the matter you want. You can add some baryons, you can add some Dirac field, you can add some electromagnetic field, etc. This is all that part there. With the equation of motion, yes. So if you want to say it on shell, yes. But at this level, no. Then after that, you get an equation which tells you that matter produces curvature. That is true. But that depends on the theory of gravity you will look for. Different theories will tell you how much curvature you will produce. But at this level, they are independent, of course. Then just the equation of motion relates one to the other, actually. Put some kind of relation between them, which is just the differential equation, the Einstein equation. Yeah. But at this level, they are completely independent quantities. So these are called the Christoffel symbols. This is not a tensor. So imagine that you have a space-time, you have some metric, then you just make some derivatives, etc. You have the Christoffel symbols. If you have the Christoffel symbols, you can calculate the Ricci tensor, etc. So then you complete completely this idea. And the signature that I will take is the signature minus plus 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 of the metric, which means that if I take, for example, the Minkowski spacetime, it will be this minus plus 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 plus. In particle physics, they use usually the opposite, plus, minus, minus, minus. But for me, in gravity, we use actually this definition to keep space with the right sign and time with the minus sign, actually. Okay, it's just a matter of definition. You can take the other one, it will be exactly the same. And you can write it in spherical coordinates if you want, and you will just have something like that. Okay, so that is the geometry, and more or less this is the structure that we will use. You have all the complicated part is to find this, to find the metric. That is the tough part, and this is what we are looking for. And the metric tells us the distance between objects and things like that. But if we had the metric, we can calculate this. They are just derivatives. We can calculate the curvature. We can calculate everything. Then it's just a matter of calculations. Okay.
In most of the book, R mu nu is just negative of what you have written.
Yes, no, yeah, there are two types of books. For me, so I used the book by Wald, which is General Relativity. So for the definition I'm taking, I always used actually this one. And this is very often the definition. The other one is Misnerton and Wheeler, which have used another definition. So yeah, at the end, if we put a minus here, then we can put a minus in the action, etc. At the end, of course, the physics is independent of that, so we can use the definition we want. At the end, we have to be consistent. If you take a definition from one book, don't take the definition from the other book for things, etc. Otherwise, you start mixing and it doesn't work. But if you start with a book, you end with this book, and you go only with it. Okay. So these are just the definitions. And okay, so as I said, you will have all calculations in my notes. Let me just continue there on the variation of the action. So if I calculate the variation of the action principle in order to calculate what is finally the equation of motion, this constant doesn't change. I will have to make a variation of square root of minus g. I will get something like that. And plus the variation of the matter part. So doing that, this is where this is tricky. Actually, it's not exactly that. You have an additional term. I will talk about it later on. This is the Gibbons-Hawking term. But otherwise, this is what you have here at this level. So now if you write this equation, what you get is C4. You ask that the variation is equal to 0. And then you get the equation R mu nu minus 1/2 R G mu nu. And this is equal plus delta Sm equal to 0. So what we do is that we define a tensor T mu nu, which is minus 2 divided by square root of minus g delta Sm of delta G mu nu. So taking this, actually, you have the square root of minus g. Here there is the variation of G mu nu. So then you get the Einstein equation, which is R mu nu. So I'm passing a bit fast on that because the lectures are not really on that. But if you need it, we can either talk about it later, or you can also use any textbook on that. And you get the famous Einstein equation, which then answering or just continuing on the comment you were saying, if you have some matter, this is the energy momentum tensor, which tells us about actually matter field. So if you have some matter, the matter will produce some curvature here. So in this sense, now they are related. There is a relation between them. Every time I put some matter, I can produce actually some curvature. Okay, so this is the Einstein equation. Up to now, I don't know if you have some questions.
Sir, why we are putting this variation equals to 0? What is that?
This is actually the. I will come back to this point later on when I will add the boundary term, the Gibbons-Hawking term. But this is one of the fundamental things in physics that you say that imagine that you have 2 points here, Q1 and Q2, and you want to know what is the path between these two. So you can have this path, you can have this path, etc. So this principle tells you that you have an action or you have a Lagrangian, and you try actually to minimize this action by finding what is the path actually between these two by having these 2 points which are fixed. These are the boundary conditions.
I think in classical mechanics we say Hamilton principle, no? That is.
Yes.
Yeah.
Yes. So I don't know if you have studied that. No? No. So I will come back a bit on that when I will add the boundary term. But that is not different than classical mechanics. For the people who didn't see that, look to some book of classical mechanics. And in the chapter where there is Lagrangian formalism or action, or the action actually, and from the action actually you can derive the equations of motion. It's a quite powerful thing, in the sense that first you have.
Mic because it's not clear audible. Mic लेकिन आवाज नहीं आ रही.
Is it working? No, it's not for public, it's just for the camera.
Give color mic because it's not.
Okay,
we need
sure.
better audible. Use continue.
Okay, sure. So what I was saying. Yes, the thing is that we have. Let me just comment about that. Is that first we have the Newtonian theory. Newtonian theory tells us that we have forces, and if you make a summation of all forces, it's equal to mass times acceleration. So this is a way to have the equation of motion. Now, in the 19th century was developed a new formalism, which gives you the equations of motion from another thing, which is Lagrangian or Hamiltonian. And in which sense it is maybe more fundamental is that in this case you are not talking about forces. You are talking only about energy. Lagrangian is defined as the kinetic energy minus the potential energy. And at the classical level, both are equivalent, in the sense that you have one formalism, you have a second formalism. Both of you, they give you the equations of motion. What you want in physics at the end is the equation of motion, and then you study it. Okay? So how you get the equation of motion? Either you start with Newtonian formalism, forces, or the Lagrangian and action formalism, where you talk about energy, kinetic energy, potential energy. Now, at the classical level, it's just a matter of taste. And actually, this formalism is better because it's much simpler to find equations of motion. If you take, I don't know, a pendulum, for example, and you take 3 or 4 of them coupled, it might be very difficult to find all forces and things like that. If you use Lagrangian formalism, kinetic energy is pretty simple. Potential energy also is very simple. You can write that and get the equation of motion. At this level, it's just a matter of taste. Now, at the quantum level, it's much more fundamental to use that. The reason is that if you take an experiment, which is this Aharonov-Bohm experiment, which is telling you that the Aharonov-Bohm experiment is, imagine that you have these experiments where you send some light, and it passes through 2 actually small holes like that, and then you have actually something where you observe it, and you will observe some interferences. I don't know if you have studied quantum mechanics. Yes? Okay. Now, imagine that you put something here. The Aharonov-Bohm experiment, AB experiment, is to put here this, how do you call that? This,
Solenoid.
huh?
Solenoid.
Yeah, thank you. The solenoid, which is actually producing, there is a magnetic field inside, but the magnetic field outside is 0. But actually the magnetic field is 0, but you know that magnetic field is related to some potential vector. It's the rotational of A. This vector here is not 0. Okay? And the interesting thing is the following, is that if you think of it in terms of just classical mechanics, you would say, okay, the magnetic field is 0. In classical mechanics, we talk about forces. In this case, is Lorentz force. It's equal to Q times electric part V vectorial B. It's Q E plus V cross B. Actually, you have only this. You don't have electric field, you don't have magnetic field outside, so you don't have forces, so nothing will happen. But we know that these interferences will change because A is different from 0. And in the Lagrangian formalism, you don't have the force E and B, but in the Lagrangian formalism you have the energy, and this is A which appears. A and phi, the potential associated to the electric field, which is minus gradient of phi. So in that sense, maybe quantum mechanics is telling us that one formalism is more fundamental than the others, and forces don't really exist. What exists actually are energies. There are more these things which are fundamental objects, the energy, not a force. A force is just something that we produce ourselves mathematically, etc. But the very fundamental objects are energies, and this formalism will be more fundamental. So at the end, even if you want to build some quantum theory of gravity, better to start by a Lagrangian, by some action. At our level, we are at the classical level. We will use just the equations of motion. So this is a way to do it, but okay, there is no other way actually in this case. There is no forces. But actually it's an interesting formalism, so you can just take a book in classical mechanics and see how this variation works actually. It's pretty simple, but very, very interesting actually, very powerful. Okay, I don't know if there was some comment.
You could derive these equations through this action, but also you could use Poisson's equation. You can start with something more mundane and still arrive at the same equation, which I think Einstein did first.
Yes, exactly.
This was sort of parallel thing which Hilbert was doing.
Exactly.
What is the deep reason that these two disparate methods appear to give, don't appear, do give the same equation of motion?
You mean the
Poisson equation,
yes.
more classical, no action, and this is more deeper, the Hamiltonian action principle is involved. They are giving you the same equation of motion.
Yes.
At the end of the day.
Yes.
What's the deep reason?
I mean,
different things.
they give the same equation of motion because we choose a very, very specific action which gives that equation. But I can change the action, and this is what I will do during these lectures, where I'm not going to get this action, this equation, sorry. I'm going to get something else. So in that sense, Hilbert was good enough because he was listening to the lecture, one of the lectures by Einstein, where he was explaining that, and then he started working on that, and he got the action, the exact action which gives this equation. So it is built in such a way that it gives the same equation of motion. But I will then start doing some other actions, and they give, of course, an equation of motion completely different. But this is true that historically, Einstein developed his theory not from action principle, but starting by the equations of motion, most exactly the Poisson equation, which tells you that if you have some density of matter, it produces some gravitation potential, the Laplacian of the gravitation potential. And from that, what he wanted is to have a theory where there are tensors which appears, because he doesn't want something which depends on the observer, on the system of coordinates, etc. So he wanted something which is built at the level of tensors. And with that, he started building this, and he found that actually he was not the only one. There are some other people who developed some other theories, but never worked actually. So then step by step he started building this, and in most of the textbooks in general relativity there is a chapter on the history of it. How do you start from the Poisson equation, and then step by step you build the theory. You will need also what is known as the geodesic equation. The geodesic equation has been very fundamental into that, and linking actually the metric to the gravitation potential. So the metric here tells us about gravity. This is the gravitation potential actually, the G00. Exactly. Okay, I don't know if there are some questions, comments. Okay, so let me continue. This is just actually the basic definitions, and the T-mu, the matter part. The matter part. So I will use mostly, I mean, when I will talk about black holes, it will be vacuum. But otherwise, what I'm going to do for cosmology is to talk what is called a perfect fluid. So a perfect fluid is just characterized by its density. So you have a fluid with some density and some pressure. This is the only thing, and it has some velocity. So then you can write it like this. Otherwise, you have two additional terms, which are some stress tensor and some heat flux. But for us, we will just go with that. In the notes that I will give you, there are a bit more details about all this, etc. I didn't add references because you will find it in any textbook. And but otherwise, actually, there are more or less all the definitions that you need. So let me just try to advance a bit because we have just half an hour, unfortunately, more, something like that, like 40 minutes. Then we continue this afternoon. But on the cosmology, let's start with that, and then later on we'll continue on some other aspects. So first of all, in cosmology, when we are talking about cosmology, we are talking about extremely large scales. The smaller scales is more like astrophysics, actually. Let's go a bit to the cosmology part. So the idea of cosmology is that we are talking about very, very large scales. At small scales, things are very difficult. We have to go to nonlinear physics. But at the very large scales, when we look to the universe, it looks homogeneous and isotropic. What does it mean, actually, this? One is based on real observations. The other one is based more into with some philosophical aspect. The isotropy is something that we can measure. When we observe around us, we look in different directions, and we observe that the galaxies, they are going far from us with some velocity. And with that, we can measure something which is called the Hubble law, which has not been derived by Hubble, but which says that the velocity for the objects which are not too far from us, that the velocity of the object is proportional, its velocity is proportional to the distance. When the distance increases, the velocity increases. And the factor of proportionality is called the Hubble constant. Now, you measure actually this, and you get the Hubble constant in this direction. You get it from this direction, and you will get exactly the same thing. They are all going far from us, statistically, with the same velocity, with the same law. So actually, it's isotropic. There is another thing about isotropy. There is a light that we receive which comes from the very early universe, which is called the CMB. And this light, actually, that we receive has some temperature, which is 2.7 Kelvin. And it comes from different directions, and we observe it with extremely well precision now, and we see that it has exactly the same temperature with fluctuations which are very small. So actually, isotropy looks very well in the sense that I'm observing the universe in this direction, this direction, this direction, exactly the same. Now, homogeneity, so isotropy is related to rotation, symmetry by rotation. Homogeneity is related to symmetry by translation. I'm here in this part of the universe. If I go somewhere else, if I go to some other galaxy and I observe the universe, I should see the same. So it's invariant under translation. And the thing is that this we cannot check it. We have to go to another galaxy to check that. Actually, it's more a principle, a philosophical principle, is to say that we are not in a very specific place in the universe. Any place in the universe should be like ours, actually. So it's more like a philosophical idea to say that we are not in a very specific place. If I go to another galaxy, I should see the same. Why should I be at the center of the universe, for example? So homogeneity is more like a philosophical idea. Isotropy is something that we can check more easily. So we say that the universe is homogeneous and isotropic. Mathematically means that the space-time is invariant under rotations, that is isotropy, and translations, which is homogeneity. So actually with that, you can build a metric. And if you haven't seen that, you have to look to textbooks with an equation. I know that very often people don't introduce it in this way, but this is the only mathematical way to introduce it, using what are known as the Killing vectors and the Killing equation. This is the only way to get the metric. The other ways is more by hand, saying, yeah, if we consider homogeneity and isotropy, we get a universe of this form. But the real way to do it is actually to consider something. So this also, you will have it in the notes, actually. So I'm just going to say what it is here, and then you will work it out in the notes. There is the full calculation actually. I put it completely because you will not find it in most of the textbooks, so at least you will have it somewhere. A killing vector is telling you a symmetry. So for example, it's a vector. So if you have a killing vector in the direction of time, it means that you have a symmetry in time, that the space-time doesn't depend on time, it's static. If you have a killing vector like this, means that you have a rotation, a symmetry by rotation. So the killing vector tells us about symmetries. Here we are talking about 3 rotations that we have and 3 translations in x, y, z. So we have 6 symmetries in our space-time. And each of these symmetry means that there is a killing vector. Usually the killing vector is written like this. So this is called a killing vector. And actually, you can show that they are solution of an equation of this form. So they are solution of an equation of this form. That is always true, and this is called the killing equation. Okay, so actually this is the covariant derivative. I might not have introduced it. So it is a normal derivative minus the Christopher symbols. Okay, so having this equation actually and having the killing vector, for example, you want a symmetry in the x direction. So what it says is that you have a vector, a killing vector, which is this 0, 1, 0, 0 time x, y, z. So you have a vector in the x direction. So that is a killing vector, which is the killing vector of translation in the x direction. Sorry, there was a question, a comment? No. So you have actually this killing vector. Now, if you replace it in this equation, you will find some constraint on the Christoffel symbols, which means on the metric. So working out this, and you will have all the details in the notes, you will get that actually it means that your metric, you will get some equation like this, that the derivative with respect to x of g mu nu is 0. This is what you will get. So it means that your metric doesn't depend on the x direction. So if you have a translation in the x direction, symmetry by in the x direction, means that the metric doesn't depend on x. And you can find also the killing vector in the y direction. You have symmetry in the translation, by translation in the y direction, in the z direction. So it tells you that the metric doesn't depend on x, y, and z, so it depends only with respect to time. And now you have also rotation. So you have the killing vectors associated to rotations. Rotation in the plane x, y, around the axis z, around the axis x and the axis y. So you have the different rotations. And also you write the killing vector for each one and you find the constraints on that. And following all these calculations, it's a pretty direct calculation, you will find at the end what is the form of the metric. It doesn't tell you the full metric, but it tells you more or less its structure. So doing that, you will get at the end that the metric should have some structure like this. And this comes with 2 unknown functions, nt and at, which are unknown functions. And actually, this comes only from the symmetries. You don't have to do anything else. Just you assume 6 symmetries, homogeneity, isotropy. This is related to homogeneity. Isotropy is rotation. And you get this metric, actually. So this is very important tool because the metric from which you start is related to the symmetries of your space-time. So if tomorrow you want to work with a space-time which is anisotropic, or which has a symmetry only in the x direction, but not in y and z direction, and things like that. What is the form of the metric? So this is how you do it. You take the symmetries of your space-time, you calculate the Killing equation, and you will find a constraint on gamma, which means on the derivative of the metric, and from that you get this equation. So it's quite straightforward, and you will have all details on the notes also.
Excuse me, can
Yes.
you just elaborate on rotation and translation, which you are relating with homogeneity and isotropy?
Yes. What I'm saying is that so our space-time, we want it to be, first we want to be invariant under rotations, that we observe the universe the same in all directions. So it has to be invariant 3 rotations. One rotation is around the axis Z, and that actually gives us a Killing vector, which is x dy minus y dx.
Okay. And similarly for x and y.
Exactly. So then we have this one and this one like this. And the translation is just a shift in one of these directions. So the Killing vector will be dx or dy or dz, which is just the symmetry by translation. So each of them is the Killing vector, which is written in a basis like this. So this one will be k mu equal to 0 in time minus y x 0. So that will be the Killing vector associated to rotation and the z-axis. So we have 6 symmetries for this space-time. The maximum number of symmetries in a space-time that we can have are 10. But for this one, we will have only 6 actually, so it's not what is known as a maximally symmetric space-time. Okay, so after doing all that, you get a metric here, and this is called the Friedmann space-time, or the Friedmann, Lemaitre, Robertson, Walker space-time. Okay. So Friedman and Lemaitre did it more from a physical point of view. Robertson and Walker, which were mathematicians, they formulated it in a more elaborated structure in this way. Okay, so let me go into the Friedmann equations now that we have the metric. So we have the metric. And having the metric here, what we can do is that we can redefine time. So I will define some time t, or dt, which is equal to nt dt. So this is just a redefinition of time. We know that time depends on the observer. This is a relativistic theory. So I will define an observer which has exactly this time. So with this, actually, I can kill this. Okay. So then I have just a structure like that, which is called the Friedmann universe. So this is really the Friedmann universe. So, and that is going to be our starting point today, and now I will start going a bit more into maybe doing the calculations myself, okay? So I don't know if you have questions up to now, getting the Friedmann universe. I don't know if you have done it usually. Some have taken a class of cosmology. There is the book by Plebanski. Plebanski has a chapter on that. It's called Introduction to, the book is Introduction to General Relativity and Cosmology. And this is the East European school, which is mostly mathematical, and they explain this part about symmetries, actually, the isometries of the space-time. Okay, so having this, now what is, we have a metric, which is this. Remember that if we have the metric, we can calculate the Christoffel symbols. If we can calculate the Christoffel symbols, we can calculate the Ricci tensor, the curvature scalar, etc. So we have all this part. Then we just have to add the matter sector, and then we have the equation which are known as the Friedmann equations. So this is now the objective, is just to get these Friedmann equations, which are the equations which are telling us about how the universe is growing. Let me just maybe comment about that. if I remove this factor, I have Minkowski spacetime. Minkowski spacetime is flat spacetime. It's the spacetime that we use usually in Newtonian physics. There is nothing which is happening. We have time, we have space. Of course, time is not exactly a coordinate like space. You see that there is a minus sign that says that space and time are different. But otherwise, it's exactly, I mean, they all have a factor 1 in front of them, etc. And that, I mean, for the people who really don't know this part of geometry, let me just say that when you take, for example, 2 points here, and you have some distance here dx and some distance here dy. So what is this distance here? It's dx squared plus dy squared. This is the distance squared. So we write it like this. So this is just this dx squared plus dy squared, and this is actually the distance between these two objects, the infinitesimal distance. Now, if you have 3 coordinates, you can add a plus dz squared. Okay. So this is actually this part here. This is just the distance between 2 points in a Euclidean geometry and very flat. Now, what Minkowski did is to add time. So when we have space and time, I can measure a distance in space-time, not only in space. So you have to add a minus dt squared, actually, and that is what is including time. Now, in this universe, it's not exactly this. So you see that this is a distance between 2 points, but I multiply it by some function of time. So actually, this distance is multiplied by a factor which changes with time, which means that it will change over time. So that is the Friedmann universe. That is what is going to describe the universe in the sense that we have a universe which is going to expand, actually. So the distance between a galaxy and us, for example, will increase with time. It could also decrease. That will be called a big crunch. But we are in a universe which started from a Big Bang and which is expanding. So this is the logic of this factor here, which is called a scale factor, which is telling us how fast the distance between 2 objects actually is growing. So we have Euclidean geometry times some function of time, which is actually stretching the space-time. So space-time is dynamical, and it's actually expanding by this factor. So all the objective of the equations of general relativity, the equation of Einstein, is to find what is the scale factor here. So when we will go back to this equation here, the only thing which is left is a of t. So we put all this in this equation, and we will get some differential equation for a of t, and we will try to find what is a. Now, of course, this depends on matter. If I put some dust in the universe, I have some expansion of the universe, and we will find something. If I put some radiation, some photons, I will have another expansion. So, of course, it will be a differential equation, and this scale factor, so how fast or slow the universe expands, depends on the matter sector. This is exactly what Einstein tells us. So then we will see that some problems will arise, because if I put matter, the universe is expanding, but it's expanding slowly. If I add radiation, the universe is expanding, but it's expanding again slowly. But the problem is that we observe since now, I mean, we know it since 98, but it's more than 4.5 billion years ago, that the universe is not actually just expanding, it's accelerating. So the acceleration means that this A double dot is positive. That is what means acceleration. That scale which stretches the universe, actually the double dot of it is positive, means that there is acceleration. So we take a galaxy, we take us, and actually the distance increases but also accelerates. And we will see that we cannot do it only with dust, with radiation, and things like that. So some people, they say, okay, we will add some exotic matter. So we add some exotic matter, and that matter, which has strange properties, will produce the right acceleration. And some others, they say, okay, no, let us change this sector. That we take the same matter, but we will change the differential equation, and that matter will produce acceleration. So this is more or less the logic of modified gravity. We will see that in a bit more details and how this can come with problems, actually. So first of all, let us find the equation, this differential equation that I'm talking about, which is called the Friedmann equation. I don't know if there are questions about that. No? Okay. Yeah.
For the maximally symmetric space and time, we need 6 symmetries, that is isotropy and homogeneity.
No, for maximally symmetric, you need 10.
We need 10.
Yes.
What are those 4 extra?
You have the translation in time. That is another thing, which means that the space-time is static, which is not the case here because it depends on time. And you have 3 rotations, which are special rotations, which are between the rotation is between a space and space coordinate. You do a rotation like that, but you do it between a space and time coordinate, which are called the boost. So you have also 3 boosts between xt, yt, and zt. So you have these 3 boosts plus the translation in time, which are the 4 more. So these are the 10 things. And for a maximally symmetric space-time, you will have a curvature scalar which is constant, and you will have 3 possibilities. One is Minkowski space-time, one is called de Sitter space-time, and the other one is called anti-de Sitter space-time, if the curvature is positive, negative, or 0.
If you start with this homogeneity and isotropy principle and choose the energy momentum tensor, so that can we back calculate to reproduce this metric, or not from this that we are first assume this metric, then can we go reverse that we find actual Einstein solution?
Yeah. People, they call it reconstruction. But in order to reconstruct the metric, you have in a way to make some assumptions. You cannot just put matter here. You cannot just put matter and say, I mean, you can do it, but it's much more complicated. These equations are extremely, extremely complicated. And to solve that is difficult. So what we do is to assume something. And the assumptions, we try to do the minimal assumptions. So the homogeneity and isotropy is the kind of minimum thing. But of course, people went to opposite direction. So there are people working in anisotropic space, but from CMB, which are telling us no. There are all these spacetimes, which are known as Bianchi spacetime, which are telling that the spacetime is anisotropic. And this telescope, actually, the satellite, actually, Planck, is trying to measure these anisotropies. And they try to put some constraints on these models, which are called Bianchi models. And they found nothing, actually, that really the universe is perfectly isotropic. There are people who are doing inhomogeneous spacetime, so trying to break the other assumption. We said that it's homogeneous. So if it is not inhomogeneous, in the sense that, but inhomogeneous, the simplest thing will be to say that we are the center. We are the center, so why not we are the center of the universe? Finally, why not? So we are here at the center, and everything comes around us like this, in some way. So, of course, if it comes from here, here, or here, you still receive the same thing, because you have a symmetry by rotation, but you don't have symmetry by translation. If you go here, you don't see the same thing that if you are here. So you break homogeneity, you have inhomogeneous spacetime, and they try to calculate that and see how the structures they form in the universe itself. Seems to be difficult also. It doesn't work pretty well on the formation of galaxies. And of course, I'm avoiding all the discussions, philosophical discussions, on this very fundamental place that we have to put ourselves always at the center in some way. I don't think that philosophically it's interesting, but scientifically, why not? I mean, we can say, okay, let's be completely open-minded. We are the center, what this will produce. Do the calculations on galaxy formations, etc., how the galaxies will be distributed in the universe, and it doesn't look like very compatible. But people are still working on that because it's not very clear completely. Principally, the mathematical aspect, it's not very simple. So people are using some models here, that the Lemaitre-Tolman-Bondi model and things like that on these spherical objects, actually. And there is a South African school which is working a lot on these kind of aspects. Additional questions?
Yeah.
Yes?
Can you just repeat this, what you are telling others for? This 6 is okay.
Mm-hmm.
But what about T and X?
Yeah, no, this is a rotation also.
Yeah, this is
this is a rotation, but not between, the other rotations, we said that we have a rotation in the XY plan with around the Z-axis, for example.
Yeah.
So we do a rotation in the plan XY.
Yeah.
So between space, but we can do a rotation between space and time, actually. It's a very special type of rotation, which is called boost.
Yeah.
So if we demand that also the theory is invariant, the space-time is invariant, and this type of rotation, the boosts, which appeared in special relativity, then we have actually 3 more rotations, 3 more symmetries in our theory between xt, yt, and zt, which are 3 more rotations. So at the end, we have actually 6 rotations. The 6 rotations that we have are in the plan xy, xz, yz, xt, yt, and zt. In each of them, you can make a rotation, actually. And the 4 translations in time, x, y, and z. So this will be the 10 symmetries, actually, of the space-time. And with this, we have everything. And there are 3 space-times with these symmetries, actually. So now that we have this Friedmann, actually, metric, we didn't say anything. We didn't use yet any equation of motion. What we are saying is just by the symmetries, we know that the space-time has this structure. So now we can calculate what I was talking about, these crystal symbols, the Ricci tensor, etc., and write the Einstein equation. How to calculate crystal symbols? I would actually suggest to never calculate them directly, because you are going to waste a lot of your time, principally in space-times which are complicated. So always use the geodesic equation. This is the best thing to get them, because you write only 4 equations, and then you have these equations. So let me first say one way to do it. One way is to say that, okay, I have my crystal symbols, which do have this this structure, actually. So I have the metric. So remember, this is our metric. So the metric means what? That it's a matrix. Okay, so this will be our metric. I just wrote this thing here in form of a matrix. This is the metric. When the indices are up, means that this is the inverse metric. So when I write it like this, it's minus 1, 1 over a squared, 1 over a squared, 1 over a squared, and 0 here. So then you just do derivatives, actually. You see that the only derivative which is not going to be 0 is when you make a derivative with respect to time. If you make derivative with respect to x, y, etc., it doesn't work. So let me just write 1, and then I write the full result at the end. Let me just write 1, which is the for the people who are not from the field and who never did this calculation. Then it's just actually calculation, just mathematics. I don't know if the microphone still works. Yes, it has to be closer. So let me write actually, usually the notation is that 0 means time, means x, means y, and 3 means z. So I will calculate gamma 0, 1, maybe 0. So I just replace in that formula. It means that d0 beta, the derivative with respect to 0, g1 beta plus d1 beta 0 minus d beta g0 1. Okay, so you see that the beta comes twice. That is the Einstein notation, means that there is a summation on the index beta. When you have G0 up, the only one which is non-zero is when beta is 0. So this is 1/2 G0, 0, G0, G1, 0. Okay, so G1, 0 doesn't exist. G1, 0 is the term here. It's 0. G0, 1 is also 0. G0, 0 is -1, but if you make a derivative of it, it's 0. So this is 0 at the end. Okay, so at the end we get 0. And you can calculate for each of them. So you take here now not 0, but 1. 1, 1, 0. Then 1, 2, 1. 1, 2, 0. 1, 2, 3, etc., etc. How many of them you have? You have 40. So you spend your time doing these calculations. So how do you do it more in a more fast way? Is to write what is called the geodesic equation. Is that you define again a Lagrangian, and a Lagrangian of this form. So in our case, it's going to be minus t dot squared plus a squared of t, x dot squared plus y dot squared plus z dot squared. And now that you have a Lagrangian, which depends on what? It depends on time, and then it depends on t dot, x dot, y dot, and z dot. So you can write the Lagrange Euler equation for each of the variables, t, x, y, and z. You have 4 equations. And these equations, actually, they give you the crystal symbols directly because the geodesic equation, because if you start from this Lagrangian, you can show that at the end, the equation that you get this, you will have it also in the notes. You will get this geodesic equation. So when you take this specific Lagrangian, you derive the equations and you just identify the coefficients which are in front of it, and then you get actually the geodesic equation, the crystal symbols. Okay? So you identify them, you calculate them. Once you have these crystal symbols, you can calculate the Ricci tensor, the curvature scalar. So just to advance a bit faster, let me give you what you get. And you get this. This is the final result. So sorry for the people who didn't know this section, etc. But so I just assume that most of you have taken a class of GR and a bit of cosmology. Cosmology is not fundamental, but at least a bit of GR to know what is a metric, etc. So then you get actually the two things. One is that R00 minus 1/2 R G00. This is equal to 3 A dot squared divided by A squared. And R11 minus 1/2 R G11 is equal to minus A squared. And then this, I will call it 3H squared, where H is what I will call A dot over A. And this I'm getting here 2H dot plus 3H squared. Okay. So with that, we calculated actually, and this is the same for 2, 2, and 3, 3. R2, 2 will be exactly the same, and R3, 3 exactly the same. So with this, we calculated completely the left side of this equation, of the Einstein equation. And now this part here, we just need the T mu, the matter sector. So we put some matter and we see what are the differential equations we get, which are these equations here. So far we have assumed two things. One is Einstein's equation, Einstein theory of general relativity, and we'll see if it works or not. And two, we have assumed homogeneity and isotropy. This is the only things we assumed, okay? And with that, you can build the equations. So what is left is just the matter sector. I don't know how much time I should still.
5, 10 minutes.
5, 10 minutes? Okay. So let me just finish on the T menu, and then I think I can stop here. Yes. So as I said, I wrote at the beginning the Einstein equation, the energy momentum tensor for a perfect fluid. Let me write it again. So if you take a perfect fluid, the energy momentum tensor, you can write it in this way. So let me give on the interpretation of that. You have a fluid with some velocity. This is the velocity of the fluid. This is the matrix R, and the fluid has some pressure and some density of energy. So that is what characterizes completely actually this perfect fluid. If you take the most general fluid, like a Newtonian fluid or any other type of fluid that you will use in Navier-Stokes equation, something much more general, then you will have to add some additional terms, which is the heat flux, because maybe the fluid has some viscosity, it loses some energy, there is some dissipation, etc. And there is the anisotropic stress, also which is telling us that the pressure is not the same in all directions. You might have some pressure in the x direction, in the y direction, and things like that, which are different. So that will be the most general fluid. But remember that we are looking to a universe which is homogeneous and isotropic, so we don't expect that there will be some pressure different in one direction than the other. So we kill just this anisotropic stress, the heat flux also, but you can add them and study what it is, and you will see that they will not bring anything in the space-time. So we just go with that, which is called perfect fluid. And then you calculate T00, T11, T22, T33, and to get the Einstein equation. So let me skip this fast. The T00, what you will get is just the density. There is a factor c squared, and T11. Sorry? No, the -1 comes with when there is a 0, 0. But here you will get just, because the U00, it will be 1. And here you will have minus P minus P, and you get only density. And the T11, actually this term will go, and you will get just P A squared. A squared of T. Okay, again, it depends on the signature we take, it depends on the definition we take. You can have minus density, but I use the same definition as I said at the beginning, the book by Wald. So to be consistent, this is what I will have. So you have this equal to what we have there with a factor which is 8 pi g of the Einstein's equation, and that gives us the equation, the final equation, which are known as the Friedmann Equations. The first equation is this, 3h squared. So let me erase that part. We have 3h squared, which is this part here, equal to, Einstein says that it's equal to 8 pi g divided by C4 times the T00, which is the density. And the second equation, which is telling us that minus 2h dot minus 3h squared is equal to this term here, so 8 pi g divided by C4 P. Okay, there was a minus here, which goes with it. The a squared, I simplify it with this a squared. So we get these two equations, and they are known as the Friedmann equations. So what they say is that if I have a fluid with density and pressure, that will produce some expansion of the universe or not. So remember that what is H? H is this. And this is called the Hubble function. So let's go back to now a simple case that imagine that there is nothing in the universe. There is no matter. So density is 0. So it means that H is 0. If H is 0, it means that A is constant. A is the stretching parameter of the scale, which is called the scale factor. So in that case, it means that the universe is not expanding. Okay, so there is nothing which is happening in the universe. For the universe to react, you need some matter. So depending on the density and the pressure, you will have a different expansion. So this is the A dot, which tells us that the universe is expanding or not. So if this is different from 0, we have necessarily expansion. So as soon as you put matter, there is expansion. Just us. We are producing the expansion in the universe in some sense. Because we are some matter, we are some density, so we produce that. So we have also an effect on the universe, just ourselves. We are not just observing it, but we are producing it in some sense. And this equation is related to the pressure, and H dot is related to the second derivative. So that will tell us about the acceleration. If the universe is going to accelerate or not, that depends on this equation. Let me just rewrite it differently to see what is the acceleration, and we will end with this. According to this definition, if I calculate H dot is equal to A double dot over A minus A dot squared over A squared, which means A double dot over A minus H squared. So we have that H dot plus H squared is the acceleration. Okay, so we want to build an equation here where there is H dot and H squared. What I can do is I make a summation of both. So I will get that minus 2H dot is equal to 8 pi g divided by C4, density plus pressure. I can divide by minus 2, so I get minus 4. So H dot is this, and H squared is 8 pi g divided by 3 C4 density. Now if I make the summation of these two, I will get the acceleration. So the acceleration divided by A is going to be 8 pi g, I will write it in this way, 3 C4. We have the density here, and I have to multiply and divide by 6, multiply by 2, divide by 2 or 2/3, minus 3/2 density minus 3/2 pressure. Yeah. So then we simplify this, and you get density minus 3/2 density is minus 1/2, and minus 3/2. I can factorize a minus 1/2. So I get minus 4 pi g divided by 3 C4, and I get density plus 3 times the pressure. Okay, so what is the conclusion? That if we want an acceleration, means that this is positive, then because there is a minus sign here, we need negative here. So acceleration of the universe, you need that rho plus 3p to be negative. Okay? So this comes from the Friedmann equation, and a direct calculation from that, which is telling us that in some sense you need some exotic matter. The matter that we know usually has some positive density of energy, has some positive pressure. So this will never be negative. If you take radiation, the pressure is 1/3 of the density actually. You can calculate it in statistical physics. And in any type of actually fluid that you know, you will always have this positive because both of them are positive quantities. So how can you get something negative? You might say, okay, I need something more exotic. So that was one direction to say we need something very exotic. Maybe we don't observe it. And this thing very exotic will produce an acceleration of the universe. I will talk about acceleration of the universe. How do we know that during tutorial, actually? We will go into with Mathematica, etc., and see that. The other thing would be to say, but let us change our equations. Let us keep density and pressure positive. But let us not make it that this is 3h squared, but I don't know, it can be plus 2h plus some alpha h dot, something like that. So then it will be completely different equation. With a density which is positive, I might produce some acceleration. Then it is possible. But to have this, I need to change the left-hand side. So this equation here, I will have to change it and to add some terms here. And that will be maybe one direction of possible direction, which we would call modified gravity. So the two directions usually are the following. One is to say, clearly we have acceleration of the universe. I will explain that more with details. We have an acceleration of the universe. We know that for sure. They received a Nobel Prize for that, etc. So it's sure. Usually Nobel Prize, they wait some number of years before giving it to be sure, not to regret it after, of course. So they observed it in 1998. They received it in 2011, so they waited 13 years. Now we know we have an acceleration of the universe. And as a theoretician, we have to explain it. So we have two possibilities. One is to say there is exotic things. I will explain how much exotic it is. And the other thing is to say, oh, maybe general relativity doesn't work because Einstein tells us that this is the equation of motion. It tells us that if we have some matter, that matter produces exactly this curvature. But some people, they say, no, maybe there are some other curvature terms. So maybe we have to add some additional terms. And we will see that this modification of gravity doesn't come in an easy way. We have always to keep in mind all the observations which are showing since 100 years that Einstein works perfectly well. They are, and recently, gravitational waves. I will talk about gravitational waves principally on Friday, and they put a lot of constraints on that. Principally, this modification of gravity, usually what they say is that gravitational waves, they propagate with some speed. And Einstein theory says that if you do the calculations, we will do it during the tutorial on Friday, that the gravitational waves, they propagate at the speed of light. And these theories, most of them, they say no, actually. They propagate at a speed which is different than the speed of light. But the problem is that it has been observed that actually that there was this merging of two neutron stars. We received at the same time light, so which goes at the speed of light, and gravitational waves. We observed both, and we received them at the same time. So clearly, gravitational waves, they propagate at the speed of light. They propagated at the same speed than gravitational waves, than electromagnetic field. So that puts a strong constraints on these theories. We will go into the details and see what kind of theories are ruled out, what kind of theories are still working, etc. But this will be into more details and calculations on Friday. Before that, I will go into most of the experiments. How do we test gravity in a lab? In a lab experiment, how do we test gravity in the solar system? How do we test gravity at the cosmological scales? How do we test gravity with compact objects? Because if you modify gravity, you can produce an acceleration very simply. You just add few terms and you have acceleration of the universe. That is the simplest thing. But when you do that, you have to be consistent with everything which has been done during 1 century. All experiments that Einstein actually passed perfectly well, we have to check them if it works or not. And we'll see that's not an easy thing, actually. So that is all the literature of modified gravity. It's not only to produce an acceleration. It's to be consistent with everything. If you want to replace Einstein, you have to be good on all topics, actually. Okay, so we'll continue this afternoon on this aspect, and then in the evening on tutorial, we will see how to calculate actually age of the universe and to put some constraints on our parameters. I don't know if you have some questions before lunch.
problem is rho plus 3p. You know that how you can make it negative.
Yes, actually, to make it negative, there are two ways. One is to say there is exotic, but we don't see it.
Yeah.
And there are different things, and we'll see that one of them actually exists, which is vacuum energy. Vacuum energy. The vacuum energy, and this is what appears in our theory as a cosmological constant. Vacuum energy is a well-defined thing in quantum mechanics, and it comes with a negative pressure. And actually, in this case, rho plus 3p is negative. So with vacuum energy, we can accelerate the universe. I will talk about it a bit in this afternoon. But there are other problems. That is what is called the dark energy problem. There is dark matter problem. There is inflation. I will also say about it more in this afternoon, actually, on these problems.
Okay.